Okay, the recording is live. Last time we met, we started our topic acids and bases, a spectrum. We immediately got a chance to follow it up with a day one of a 2-day titration experiment. So we do have a part two of our wet lab today. So before we get into the new material, and of course, talking a little bit about today's lab, just a little reminder about the content behind acids and bases, our definitions, and any relevant equations that we might use. Now, throughout history, acids and bases have taken on many definitions. It all circles back to the initially known equation where water, H2O, is known to split up into its respective ions, H plus and OH minus. From way back when, water has always been known to exhibit both acidic and basic properties. This is what's known as amphoteric. Now, based on this idea, this equation that water splits up, various definitions of acids and bases have been proposed throughout history. The first, made by a man named Arrhenius, defined acids as proton producers and bases as OH producers. However, as our vocabulary grew, as new chemicals were discovered, as new utilitarian forms of acids and bases were discovered, definitions had to evolve as well. A contemporary of Arrhenius, two contemporaries, Bronsted and Lowry, redefined an acid and a base. While they maintained the definition of an acid being some sort of source of protons, in this case, they changed it to H plus donor, they changed the definition of a base from OH producer to H plus acceptor. The reason for this, of course, is the OH producer definition worked really well for water, but as new bases were discovered, that OH producer definition became a bit limiting. Bronsted and Lowry then said, well, if our definition is true, that acid is a proton donor and bases are a proton acceptor, then the following equation must also be true, where water, again, acting as both an acid and a base, accepts a proton to become H3O plus. Someone at the same time / within 5 years, Lewis also proposed his own definitions of an acid and base. However, I believe Lewis was a trained physicist, so his definition is more appropriately used within that subject. Now, it's important to know that all of these definitions are still true to this day. Some just work better than others. For the purposes of Chem 1A, we will be sticking to the Bronsted-Lowry definition. That is where an acid is a proton donor and a base is a proton acceptor. Now, throughout last Wednesday's discussion, as well as just a while ago, you've probably noticed that I do interchangeably call H plus a proton. The reason behind this just comes down to the chemical breakdown of that hydrogen. Now, of course, neutral hydrogen has 1 electron, 1 proton, and 0 neutrons. However, H plus, having lost an electron, now only has the 1 proton present. As a result, we do interchangeably refer to H plus as a proton. And it's this very basic idea that leads us to our discussion of acid and base strength. In fact, the question is ultimately, how can we rank acids? How can we determine that one is stronger than another? Well, we remember the basic idea that acids will donate protons. So if we could measure how easy it is for that acid to donate a proton, we can, of course, devise a ranking system. This is what led to the pH scale. The pH scale is a literal scale from 0 to 14. Smack dab in the center is 7. At a perfect pH of 7, a substance is defined as neutral. That is, it is neither acidic nor basic. To the left, that is from 0 to 7, is described as acidic. And to the right, from 7 to 14, is defined as basic. Now, the pH scale does a really good job of helping us categorize acids in a very quantitative way. For example, we can say that a pH of 1 is stronger acid than that of a pH of, for example, 4. But the pH scale also tells us something really cool. In other words, as we go more to the far left, we get our strongest acids. If we go to the far right, we get our weakest acids. But the beauty about the pH scale is that it allows us to comment on both the acidic nature of the compound as well as the basic nature. What do I mean by that? Well, over here on the far left, we have our strongest acids. Since the two are mutually exclusive, we can also say that the strongest acids are our weakest bases. Similarly, all the way to the far right, we have our weakest acids. Our weakest acids are simultaneously very strong bases. So the pH scale in its own right represents a basic phenomena of acids and bases in that it is a spectrum. More often than not, a single compound can be both acidic and basic. However, it is commonly a very strong acid or a very weak base. Just as how there is a pH scale, there is also what's known as a pOH scale. However, that is dropped out of our common vernacular simply because the pH scale does a really good job of both determining acid strength as well as base strength. So while you might find some resources that still use pOH, for the most part, it has dropped out of our day-to-day vernacular. Since pH represents a numerical or quantitative measure of acidity, there exists a few equations around it. But to first go into them, we must remind ourselves that that letter P, as in the P in pH, quite literally stands for negative log. So when asked to calculate pH, it is simply the negative log of the H plus concentration. Similarly, as we have seen a pOH scale, that is equal to the negative log of the OH concentration. That is, of course, in one direction from H plus to pH. What if we wanted to go the opposite? To calculate H plus concentration, we will take 10 to the negative pH, where 10 to the is simply the opposite of log. So in other words, if I were to add something, the opposite would be to subtract. If I were to multiply something, the opposite would be to divide. If I were to log something, the opposite would be 10 to the whatever, where of course the negative it remains. The same thing can be said for the OH concentration, where the OH concentration is equal to 10 to the negative pOH. Finally, we have two more equations that relate the two in that pH and pOH, the sum must be equal to 14. And the product of the concentrations is equal to 1 times 10 to the negative 14. These equations represent the 6 primary equations we will be using when determining or commenting on acids and bases. You will be given these equations as part of your next exam. You do not need to memorize them. So let's see if we can get some practice right now using them. I'm going to have the equations right up here on top. We're going to go through a couple sample questions. Oops. Starting with a fairly straightforward one. What are the pH and pOH of a 0.0125 molar solution of KOH? That's all the context you're given. You're being asked to calculate the pH and pOH of a solution of KOH that has a molarity, a concentration of 0.0125. Recognize, of course, that based on our normal formulae for pH and pOH, let me just write them back without the purple highlighter. We have the following two equations. pH is equal to negative log of H plus, and POH is equal to negative log of OH. So in some way, shape, and form, our most default formula is to actually have either the H plus concentration or the OH concentration. However, based on the given question, nowhere have I explicitly given you the H plus concentration or the OH concentration. It's up to you to put in a little bit of effort to think this through. You see, we have here KOH. KOH, as a chemical compound, can and will split into K plus and OH minus. It has the ability to, of course, break up into its respective pieces and at the same time reform. How does this help us answer this question? Well, remember, what we're really seeing here is that we have effectively a beaker full of KOH, just KOH. And within that same beaker, that KOH does split into its K plus and OH minus. So within this beaker, within this solution, we actually only really have the one chemical. In other words, what we see here is a 1-to-1 ratio between the KOH and the OH concentration. This 1-to-1 ratio in the same beaker or flask or glassware, whatever you want to call it, is what tells us the concentration of KOH is equal to the concentration of K plus, which is also equal to the concentration of OH minus. This is all based on the fact that the only thing we have present is the KOH. And since it's known to split up into its respective ions, we can, of course, make the simple conclusion that the concentrations are equal to one another. In other words, what this tells us is that the OH concentration is equal to 0.0125 molarity. So although not explicitly told to you as the OH concentration, it's on you to recognize that KOH does split up into these respective pieces, and they exhibit the same concentration. Now that we have this number on lock, we can then plug it into our equation. We know that POH is equal to the negative log of the OH concentration. This is equal to negative log of 0.0125. If I put this into my calculator, negative log of 0.0125, I get the answer 1.9. I'm going to round that to 2 decimal places, 1.9. And with that, I have calculated the POH of the solution. Remember that POH, like pH, is unitless and is traditionally written to 1 decimal place. This isn't all the question asked for, however. You see, insofar, all we've really done is say, well, based on the KOH, we can identify the OH concentration. Based on the OH concentration, we can identify POH. That's checked off, so all that's left is to calculate pH. So you go back to your 6th formula and you say, all right, so to calculate pH, I need the negative log of H plus. So in theory, it should be the exact same process. But as you look back at your equation, the first thing you should immediately notice is that there is no explicit H plus. So that formula doesn't quite work. In fact, the only other formula we can use is this one down here that says pH plus POH is equal to 14. We know that the sum of the two values must add up to 14, such that we're able to say if pH plus POH is equal to 14, then pH is equal to 14 minus POH. All I've done, of course, is just carry over the POH. This becomes 14 minus 1.9. Let's just put this in our calculator to be absolutely certain. 14 minus 1.9 gives us almost exactly 12.1. And with that, we have now calculated both the pH and the POH of this potassium hydroxide solution. Now, all this question was asking you to do was simply calculate what are these values. Although not needed, you can make further conclusions about this solution. Based on the pH, we're able to say that since the pH is greater than 7, this is identified as a basic solution. Sure, you could argue, well, that's pretty close to 14. So you could say it is a strong base. That's absolutely fair. But at the very minimum, we can definitely call it basic. And of course, recognize that it does follow one of the definitions. KOH is a base, and according to Arrhenius's definition, it produces OH. Those latter two bits are just rather conclusions or insights that we can glean into the question based on the information, but they're not outright asked of you. Let's try another. The question simply says, what is the POH of a solution where you're specifically being told the H plus concentration is equal to 2.5 times 10 to the negative 3 molarity? All right. So a couple ways to go about this. We know our 6 equations. We have them at the ready. We have them on deck. The question is ultimately asking us to find POH, and it's given us H plus. Recognize here, there is actually no single equation that relates H plus to the POH of the solution. There is no single equation that links the two. So this is a case where you're going to need to manipulate and use both. And there are a couple ways you can go about this. We're actually going to go through 2 ways. And again, and to be clear, both approaches should lead you to the exact same answer. I'm just breaking them down to show you that ultimately doesn't matter which method you take. You just, of course, will get the same answer no matter what. One of the first things that we can do is we can say, well, we know for a fact pH plus POH is equal to 14. Similarly, I can say that POH is equal to 14 minus pH. Based on one of the formulae we just saw, this is the same thing as 14 minus, and let me use a different color here to make it clear. pH is equal to the negative log of the H plus concentration. I wrote it in a different color to make it clear those negative symbols. Remember, The letter P literally stands for negative log. So these are going to be two negative symbols together. Keeping it going, this is equal to 14 minus, I'm going to keep that equation as written, negative log of the H plus concentration, aka 2.5 times 10 to the negative 3. I'm not simplifying it just yet. I'm literally just substituting the values. Now I'm going to put it into my calculator. This is 14 minus negative log of 2.5 times 10 raised to the negative 3. The answer I see here, when rounded to 1 decimal place, is approximately 11.4. And with that, we have solved for POH using two equations that we had to manipulate together. There is, of course, another approach to do this. And again, you should get the same answer in both methods, where one of the equations we know is that the product between the H plus and the OH concentration is equal to 1 times 10 to the negative 14. We can say that the OH concentration is equal to that 1 times 10 to the negative 14 divided by the H plus concentration. All I've done so far is simply divide both sides by H plus. I can then say this is equal to 1 times 10 to the negative 14 all over the H plus concentration, 2.5 times 10 to the negative 3. Whoops. Putting this into my calculator, 1 times, whoops. Fraction. On top, we have 1 times 10 raised to the negative 14 divided by 2.5 times 10 raised to the negative 3. We see here a pretty simple flat number. This is just 4 times 10 to the negative 12. Of course, we're not done here. All this simply does is calculate the OH concentration. From there, we can say POH is equal to negative log of the OH concentration, which is equal to negative log of 4 times 10 to the negative 12. Negative log of that number. And again, we see the exact same final answer when rounded is approximately 11.4. So both approaches lead you to the exact same answer. It's just a matter of choosing the equations you want to use or manipulate. Depending on your own personal feelings, one of these might be shorter or faster than the other. Do we have any questions so far? Great. So this part has been more or less a quick recap of last week's material. After we went over the basics of pH, POH, and their calculations, we then turned our attention to a concept known as titrations. Now that you all have had in-person experience with a titration, this should make a little bit more sense to you now as we go through it. A titration, as you will perform again today, is an experimental technique that's used to determine the concentration of an acid or a base using the known concentration of another. As you all saw with some of your calculations, this really follows stoichiometry. Something else that is included in titrations is pH changes, which is indicated via color change. Here we have just a simple diagram of the setup. Now that you've actually done it in person, this should make a lot more sense to you. We have the burette, we have the flask, We add our sodium hydroxide, we wait for the color change, and we're able to gain information, which then allows us to calculate concentrations in a matter that we're used to. All of this surrounds the basic idea of a neutralization reaction. Neutralization is a concept, a term we haven't heard in quite some time. This is way back when we covered predicting products. We talked about how the reaction between neutralization is a reaction between an acid and a base that results in the formation of an ionic compound, here abbreviated as CMPD, and water. The idea, of course, behind neutralization is that these different chemical compounds, an acid where the pH is less than 7, and the base where the pH is greater than 7, eventually reacts to form products where the pH is pretty darn close to 7. Water is, of course, acts as both an acid and a base. It's right smack dab in the middle. Maybe sometimes we'll see it around 6.9. Maybe sometimes we'll see it around 7.2, but it's going to be within that nice range of around 7. An example of a question I could ask you based on neutralization is a question that you may be all too familiar with. I'm going to give you an equation. Here is the reaction between H3PO4 and KOH to give us K3PO4 and water. To balance this equation, we're going to put a 3 in front of the KOH and a 3 in front of the H2O. This equation, or this type of equation, should look immediately familiar to you, right? You should be able to understand, how did I get the products? We matched the ions, we crisscrossed. How did I know the state symbols? Well, traditionally, I give you the state symbols of the reactants, and you should predict the state symbols of the products. Water is always going to be liquid, and whether or not something is aqueous depends on the solubility rules table. So this is not some new topic I'm introducing to you, but rather I'm reminding you of it. The question is as follows. You require 0.025 liters of 0.5 molar KOH to neutralize 0.075 liters of H3PO4. What is the concentration of H3PO4? So the wording of this question should be very, very familiar. You're given some information about one chemical, and you're being asked information about another chemical. So of course, this involves stoichiometry, this involves the roadmap, but now you have in-person context. You understand innately how they perform this reaction. This is the reaction between an acid and a base, hence titration, where you know the information or concentration of one chemical, and after performing the experiment, you know the volume of the other chemical. All we're being asked to do is calculate the concentration. Let's see what that looks like. We'll be drawing a roadmap between H3PO4 and KOH. Give me a second to draw the roadmap in full. And by now, I know that a lot of you have come into your own vis-a-vis how you would draw your roadmap. It's okay if it doesn't perfectly visually match mine anymore. The roadmap is ultimately just a visual tool that's used to help gather the information and point the way forward. All right? Based on the information given, we can fill in the chart. We know we're dealing with 0.025 liters of KOH. It's already in liters, so no conversion needed. We're also told that the molarity is 0.5 m. We're told that we're working with 0.075 liters of the H3PO4, so we write that in as well. What we're being asked to find is the molarity. With this, we see the path ahead. We're going to go volume to moles, mole ratio, then moles to molarity. Based on this, of course, we do not need the top half of the roadmap. Maybe you already identify that. That's good with me. But we're just going to erase it to increase transparency. The only thing missing, of course, is me explicitly reminding us what our ratio is. Based on the given equation, we see that the ratio between H3PO4 and KOH is actually going to be 1 to 3. Remember, it needs to be in the appropriate order, although it doesn't matter which one you put on the left and which one you put on the right here. The order of ratios does matter. There is 1 H3PO4 for every 3 KOH. So please do not write it 3 to 1 because that would be in the wrong order. Based on this, we can now attempt to solve the question in full. We have our steps labeled 1, 2, and 3, starting with step 1. We're going to go from volume to moles, specifically for KOH. Number of moles is equal to molarity times volume. The molarity is 0.5. The volume is 0.025. If we put this into our calculator, 0.5 times 0.025, we get the following number, 0.0125. We can immediately write that number into our charts. Now we have here a situation where the number is a 1 to 3 ratio. Remember what that means. 1 to 3 is the same thing as 2 to 6. It's the same thing as 3 to 9. So think about the direction you're going. If you're going from 1 to 3, you actually multiply by 3. But we're actually going the opposite direction. So we're actually going to be dividing by 3. Dividing that number by 3 leads us to a pretty small number. Let's write that into our brackets here. This is 0.0042. Notice I did simplify it to get to 2 significant figures, 0.0042. And of course, all that's left is to go from moles and volume to molarity. So the third step is to go from moles to molarity, this time specifically for H3PO4. Molarity is, of course, equal to number of moles over volume. The number of moles is 0.0042. The volume is 0.075. It's already in liters, so no conversion needed. Putting this into our calculator, 0.0042 divided by 0.075 gives us an almost exact number of 0.056. 0.056 molar. So something I immediately want you to understand about at least this specific type of question is that it's something that you've gotten used to. We've conducted about 2 exams at this point already that do involve the roadmap in some way, shape, and form. So we're just tying topics together. Does anyone have any questions? Yes, Catherine.
Give us the pH formulas.
Yes, you will be provided with all 6 of these equations as part of the reference sheet. Like last time, I'll be sure to print it ahead of time so you can see exactly what formulas you will have. Any other questions? Okay. Continuing our discussion of titration, we now turn our attention to a new topic, titration curves. Titration curves, in essence, plot the pH of a solution versus the volume of titrant added. Where titrant, of course, or at least in this case, refers to what's in the burette. It's what you're adding. The shape, or not rather the shape, let me say the scale of these curves depend on strength. However, the shape remains consistent. So let's see a couple examples of what this looks like. We're going to draw 2 curves, 2 graphs. You know our traditional X and Y axes, so I'll give you all a second to draw it yourselves. On the Y-axis, in both cases, is the pH. On the X-axis, in both cases, is the volume of titrant, which is the name given to what's in the burette. While pH is unitless, volume can, of course, be in milliliters or liters. In other words, we do traditionally know the units of volume. This depends on whether it's in milli or just regular liters. And we're going to look at in total 4 graphs, but right now we're focusing on 2 of them. Over here on the left will be the reaction between a strong acid and a strong base. One on the right will be between a weak acid and a strong base. And the only thing we need left right before we actually start drawing the graph is just to put some numbers on the y-axis. We'll just arbitrarily put 1, 7, and 14. We'll try to draw them at least some distance apart so we know how wide it could be. 1, 7, and 14. Yet again, it just We just slightly put some numbers. It doesn't need to be perfectly to scale, but it just allows us to understand where our numbers are. So traditionally, I'll probably say this pretty much all the time, the titrant will be your base. Pretty much all the time. I would probably say 99% of the time, the titrant will be the base. If you recall, you had sodium hydroxide in the burettes, and then you added it to a solution of acid. At the very, very beginning of this process, we can comfortably say the pH of the flask is acidic. At the very, very start of the reaction. Remember that you're adding sodium hydroxide to a flask. At the very start, the flask is acidic. We know, of course, since the label is strong acid, we know it's going to be pretty darn close to that one. Again, it doesn't need to be perfectly to scale, just as long as it's very clearly strongly acidic. Meaning, based on the scale right here, if I started it right here, that would be wrong, just because of where I drew the 7. By the time the reaction completes, aka when the color changes, we're expecting a pH of around 7. Now, that is, of course, when the color change takes place. You all remember seeing that pink or that faint pink solution that occurs around a pH of 7, maybe 6.9, maybe 7.1, but around 7. Technically speaking, we are allowed to keep adding the base past that point. Remember, in reality, you're going to stop at that faint pink, but in theory, you could keep going such that eventually you end up with a very strong base, a pH of around 14. These are the 3 different points on this graph. The flask at the very beginning, when the color changes, and of course, after you just keep adding base. All of this together leads to the following graph that looks like an S. The reason, of course, it's a curved S instead of a jagged line straight through is just because of the way these reactions work. The curve implies a little bit more gradual incline. So this will always be a curve. Let's see what this would look like for another situation. However, this time we have a weak acid. All right, well, the key difference between a weak and a strong acid is, of course, the pH. If really low is strong acid, and let's say a little bit higher is a weak acid. Let me zoom in here. Remember, according to the pH scale, at that pH of 1 is our incredibly strong acid. At our pH of 7 is that neutral species. And at a pH of 14, this is our very strong base. So our weak acid will probably be somewhere between that 1 and 7. Now, recognize that the drawing is very subjective. That's one of the reasons we put these numbers here, because if I were to grade your drawn graphs, you could argue to me, well, Supreet, based on how I drew it, I thought I was putting it closer to the 1. That's fine. But something I like to do to make it abundantly clear to whoever is grading it is I just put a random number beside the start. 5. 5 is very clearly nowhere close to 1. It is something you can objectively say, yeah, that's weak. Does it matter that we don't know for sure it's exactly 5? No. We're just drawing a graph to see what it would look like. As we continue adding our base, that color change, of course, happens around 7. Doesn't need to be perfectly 7. It could be a little bit higher, maybe 7.1, but around 7. And of course, as we continue adding base, we get incredibly basic. 14. Again, we have our 3 points. We have our flask, which has that very weak acid. We have our middle point, which is when the color change takes place. And we have when we keep adding base. Yet again, we can now draw a curve that looks like that. The shape remains the same. They're both S-shaped curves. They will always take on that S-looking type graph. But the difference is the scale, meaning the numbers. When we have a strong acid and a strong base, we're talking between 14 and 1. When we have a weak acid and a base, we're talking a slightly smaller graph. Does anyone have any questions based on this? Okay. This is the case where we changed up strong or weak acid. Now let's draw 2 more graphs. This time we're varying the base. We know what our graphs are going to look like in theory. The y-axis is pretty consistently pH. The x-axis is the volume of base added. Remember, previously we called it titrant, but like I said, it will pretty much always be the base. So we're just going to go ahead and write base. Volume of base added, which of course will either be in milliliters or liters, but it's units that we know. And of course, pH is unitless. In this case, we will be looking at a strong acid added to a weak base and a weak acid added to a weak base. Remember, in the previous 2 graphs, the bases were strong. The acids changed. Here, we now are working with a weak base and changing the acid strength. Let's put some numbers on our graphs, just putting arbitrarily 1, 7, and 14. Just so I have some space, I know what we're working with to draw. And of course, right now, every graph will have these pieces in common. The axes, the scales, the units, whatever. What matters, of course, is the scope. Without even going into detail, we know already that these graphs are going to look like an S-shaped curve. Remember, the shape remains consistent. We just want to know what the scale of it is, what the size. So starting with the one over here on the left, strong acid, of course, we start pretty low. Our color change, that's probably around 7. And we're going to keep adding base, but this time, we're not dealing with a strong base. This time we're dealing with a weak. So am I going to draw it all the way up to 14? No. Probably a little lower. Just as we arbitrarily defined a value in the previous case, let's just put this as arbitrarily 9. Why 9? I just picked a number. It just helps me understand the scale I'm working with. And of course, we know the shape will remain like an S. The S shape is maintained, but the scale has now changed. Now let's do weak acid and weak base. Tell you what, why don't you try for the next 2 or 3 minutes, attempt yourself what you think this graph is going to look like. We've been through 3 examples together. You already know that it's going to look like an S, but take a guess what you think it's going to look like in terms of scale. Take about 2 minutes to do that. And then we will go through it together. Okay. Let's see if we're on the right track. So remember, we're adding the base. So at the very, very start of the reaction, we have our acid, but it's weak. If you recall, the number I'd arbitrarily picked previously was a 5. So let's pick it again. So we know where we're starting. Color change is around a pH of 7. So just picked somewhere in that middle right there. And then as we continue adding base, it's going to get basic, but not super basic, rather weakly basic, around 9. Upon identifying those pieces, we connect it into an S. And here is our graph, our titration curve. There are a couple of things I'd like to point out specifically. Throughout our discussion, when we've talked about that color change area, we've just said, yeah, it's around 7. We haven't quite cared too much about if it's perfectly 7 or 7.1, maybe 6 point, whatever. The reason, of course, is once you draw the graph, that downward slope right here, that's where that color change happens. In fact, this region is what's known as the equivalence point. And this is something that all of these graphs have. It is described as the steepest part of the curve. We talk about how that midpoint, we expect it to be around 7. Well, more often than not, getting it to be exactly 7, I mean a flat 7.00, is pretty challenging. So we just refer to it as the steepest part of the curve. So we can label over here as well as the equivalence points. I'm not writing anything new. I'm just going to put all these graphs together. Just give me a second to do that so we can talk about it. Okay. Okay, and then just put these two graphs right here. Great. Let's see if I can move these around. Oops. Okay. All right, just to kind of aid up some clarity, let me just move some text out of the way. That way we can still refer to it. Strong acid, strong base. Whoops. Weak acid, weak base. Okay. There we go. And now it's a little, it's of course the same figures we've been dealing with, but they're just a little bit spread apart. Now, hopefully, once we see all four together, at least on the same sheet or same page, we can understand visually the differences between the four graphs. They're all S-shaped. They all have those big pieces. They will all start in that acidic area. They'll all end up in the basic area, the scale of which just depends on the strength. There are two ways, of course, you know what the strength of an acid or a base is. You can calculate the pH. That should give you an exact number. There is one other way that you can determine strength of an acid or a base. And actually going back a couple of bits to last week, to this table. Last week, I'd given you a chart containing the most commonly encountered acids and bases we will see this semester that ranks them as either strong or weak. Way back when we talked about how I do expect you to commit this chart to memory. You can, of course, kind of devise your own mnemonic to figure it out or whatever, but you will be expected on some level to be able to identify strong and weak acids and bases. Let's see how that would work. Just going to copy this back so I don't need to keep flipping pages back and forth. Here are a couple questions. Plot a titration curve for the following reactions. First up is AlOH3 and HClO4. Second is calcium hydroxide and CH3COOH. And let's just do, plot a titration curve for the following reactions. Okay. So let's do the first one together, and then you will attempt the second one on your own. The question is pretty bare bones. It just simply says plot a titration curve. maybe if I'm being a little bit more specific, I just need you to sketch a titration curve. Sketching, of course, implies that I'm not expecting anything to be drawn to scale. I'm just looking for what I expect the graph or the curve to look like. Plot makes it sound like you need to give specific numbers and it needs to be perfectly to scale, all that. I'll probably just say sketch. So to sketch a titration curve, of course, fundamentally, we understand that it's going to take an S-shaped curve. We know that already. We know that the y-axis is going to be pH. We know that the x-axis is going to be volume of base. These are all pieces we know already. What we need to know or figure out to the success of this reaction is exactly where on the scale this acid and base will be. To do that, we will refer to the charts. First up, we have aluminum hydroxide. A quick scan of the chart actually places it here in our weak base section. That's how we know that our aluminum hydroxide is a weak base. I'm just going to label it WB, weak base. And then we have HClO4. Again, scanning the chart, we see it up here in the strong acids section. That is what tells us HClO4 is a strong acid. Just going to move this bottom question out of the way so I have some space. We know, of course, our graph, what we know it's going to generically look like. We have pH on the y-axis, volume of the aluminum hydroxide added. Remember, it's not generically base anymore. We already know what the base is. So I do expect you to include that specific label, meaning if you just wrote the word base, if you were the only person that did that, I'd take off like a point or two. But if many people made that mistake, I'd probably ignore it. But I do expect you to incorporate the name or the chemical. We're going to just draw in generically 1, 7, and 14. That way we just have an idea of where everything is located. Again, it doesn't need to be perfectly to scale. And we're just going to sketch the curve. We know at the very, very beginning, we'll have nothing but acid. We've already identified it as a strong acid. So putting it pretty low works. We know no matter what that our color change, our equivalence points is going to be around 7. And we know that as we keep adding base, we're actually going to stop pretty low. Let's just call this 9. Why are we stopping low? Why are we not going all the way up to 14? Well, this is a weak base. You could have chosen 8. You could have chosen 7.5. Doesn't matter. But the number clearly tells me, yeah, that looks weak. Finally, of course, we're just going to connect all 3. And the only label you need is that steepest point that's known as the equivalence point. And this is the extent to what I could potentially ask you of such a question. I could either ask you, draw me a graph, or I could say, of the graphs below, which one most closely represents a weak base and a strong acid? So I simultaneously need you to know how to draw these graphs and know how to identify them. Yes, Sarah.
Question. Will there be a list of strong and weak stuff?
Ultimately, if what you're asking, if I will give you this chart, I will not give you this chart. I do expect you to either memorize it, study it, know it, whatever, but you will not be given this chart. Yes, Prob? It will not be provided. Correct. With the time that we have left, let's just do part B together. This is the reaction between calcium hydroxide and CH3COOH. We know, of course, what the graph is going to generically look like, so we can just write some of that stuff in. pH on the y-axis. Volume of base added. I know we haven't yet identified what our acid and our base is. I will identify it, and then we will update. We're going to put some numbers, pH 1, 7, and 14. Now we look at our given chemicals. We have here calcium hydroxide. Hopefully you at least have that chart accessible on your end. Calcium hydroxide is over here. It is defined as a strong base, right? SB for short. Then we have CH3COOH, referring back to our chart. It's over here in the weak acids area. I just like to write WA. We're starting with an acid. The acid is weak. So I'll just put it, I don't know, let's call it 5. I know that my equivalence point is going to be around 7. And the fact that I have a strong base means it's going to go all the way to 14. Remember, of course, now that we've identified our base, we're going to update the caption, the x-axis. It is a volume of calcium hydroxide added. Once we, of course, identify those big points, we're then going to draw our S-curve. All that's left is to identify and explicitly label our equivalence points. Does anyone have any questions? Okay. Aaron represents the end of new content for acids and bases. On today in lab, we're going to finish up our titration experiments. And then on Wednesday, both lecture and lab will just be a focused workshop on acids and bases. So no new content will be taught on Wednesday, but we're doing a focused practice session on acids and bases on Wednesday. I will, of course, carry the worksheet and print it all for you. It's 1:12. I'll see you all at lab at 1:30. If you have any questions, come talk to me now. If not, see you in about 18 minutes.